So I'm going to talk about rigor and generality in Dedekind's works. So I will spend more time on rigor. But in fact, very often, if not always, in Dedekind's works, he exposes his desire to give a definition or a proof for certain concept or certain results that would be both rigorous and completely general. And so the link between rigor and generality is very noticeable and very tight, but it's never explained. So I want to try to unfold or untie the links. And I will begin with a paper he wrote with Emmylou Haffner, which is very enlightening on these issues, but not very known from the authors. So it's a paper on algebraic function theory. So algebraic function of one complex variable. So they want to give a rigorous foundation to the theory of algebraic function as Riemann did it in his inaugural dissertation in 51. So basically, they want to give a new rigorous and general definition to the notion of a Riemann surface. And so I will say more about that. So Dedekind and Weber were editing Riemann's work together, and while they were doing that, Dedekind wrote to Weber that although he knew and believed in Riemann's work, it didn't master them, and he would not master them until he had overcome, in his way, a whole series of obscurities, and for that he needed the rigor that is customary in number theory. So as you probably know, Riemann was not the most clear and the most rigorous mathematician of his time, but so less could say about him. So they want to clarify what he did, and they want to give to his theory the rigor that they consider to be indispensable to understand and to develop mathematics. So they will propose a new presentation of Riemann's theory, and according to them, so that's the very first sentence of the paper that is quoted here, they want to present a theory from the viewpoint which would be simple and yet rigorous and perfectly general. So for that, they are going to use Dedekind's method from algebraic number theory. So they are openly dissatisfied with what was done before them in Riemannian mathematics, more, with everybody who ever worked on Riemannian algebraic function. And it's because the work that were done have a tendency to admit theorem based on evidence or on intuition, and because they make a priori restrictive hypothesis on the singularity of functions, so they will have distinction of cases and things like that, and they want to avoid that kind of thing. Unfortunately, they are able to find a way to provide what they say is a more reliable basis for the fundamental notions and a treatment of the theory that is general and exceptionless. And so for that, they take what Dedekind did in algebraic number theory. So he introduced the notion of fields and of ideals, and he studied the laws of divisibility for the ideals in fields of algebraic numbers. And they can transfer them to algebraic function theory because, of course, you can define a field of algebraic function of one complex variable. So you can transfer that, and you can do the same kind of study of divisibility for the algebraic function, and from there they can propose a new definition of the Riemann surface based on the notion of prime ideal. So what they do, so the concept they introduced, so I'm not going to talk about the concept they actually introduced, but some of them are very, very close to what we do today in algebraic geometry. And so to define the Riemann surface, they use the notion of prime ideal, and they can give a completely precise functions, so no consideration on singularities or anything like that. They don't rely on the representation of the function, contrary to what Weierstrass was doing with the series. And of course, they don't use any intuition. And a large part of the paper is based on arithmetical relationships defined between IDs. So they define a divisibility relationship between IDs, which is to contain is to divide. So that's a set theoretic relationship, but they are using it as a divisibility. So that's a sort of generalization of divisibility as we know it in elementary number theory. The last important thing is that the demonstrations are not only valid in any field of algebraic function of one variable, but they also are developed on the basis of general concepts in the theory studied. So, for example, the theory of ideals in this field is given in the most general way possible, insofar as, well, you are only in the field of algebraic function of one variable. So when they present their motive for the new treatment, they talk about generality and about rigor without any distinction. And so it seems that a definition will be admissible as a rigorous definition only if it satisfies a strict criteria of generality. And so you can find the same kind of things in Dedekind foundational works, which you probably know quite well. So he wrote a book on real numbers and a book on natural numbers, and in both these books he underlines how there is no rigorous or scientific foundation for arithmetic, and it's especially because we have a tendency to consider as being simple certain notions that are not actually simple, such as cardinal numbers. And so we don't define them, or we don't prove certain results. So for example, when he defines the real numbers, he says that so arithmetic lacks a truly scientific foundation. That's his words. But of course, to give a truly scientific foundation for the real numbers, you cannot use theorem that has not been properly proved. So Dedekind will disagree with using sequences. You can't make illicit hypothesis of existence. So that's an allusion to using magnitudes that you can't define in any precise way. And of course, you can't use intuition. So Dedekind using this arithmetic notation not very that's very obvious in Dedekind work. And so he says that he wants to find a purely arithmetical and perfectly rigorous foundation for the principle of infinitesimal calculus. And he will consider that it is done in a completely satisfying way with the definition given by the cuts, which are, as you know, set theoretic tool which only necessitates to suppose the existence of the rational numbers. And of course, when you define the numbers, you suppose that the rational numbers are well defined already. And this will allow to define the irrational numbers all at once. So that's a general definition, because that's a unique definition for all the real numbers. And you can also give a definition, a foundation to continuity, which is the essential property of the real numbers. So you have a definition that is both rigorous and general, and which will allow to have a solid basis for calculation with irrational numbers. And so it will make it easier to work in analysis. Sorry. And so when you define the natural numbers, the motivations are basically the same. So he notices again that there is a serious lack of rigorous demonstration at the foundation of arithmetic. And so he proposes to define the sequence of natural integers with the notion of sets, and so he gives a set theoretical definition which is equivalent to P-n sets. And what he wants to do is to identify the mutually independent fundamental properties of the sequence of natural numbers. So he wants to find the properties that will turn into axioms. And he wants to express them in a way that diverts them of their specifically arithmetic character, so that you can subsume them under more general notions. So the more general notions are sets and mappings, and then you can have a foundation for the reliability and completeness of proofs, and for the construction of non-contradictory notions and definitions. Why do you want to divert them of the arithmetical character? That's because arithmetic is the science of numbers, so of course when you define numbers, you don't want to assume any of the properties that you will in fact deduce from the nature of numbers. So that's a point that assures the rigor of the definition, since you will avoid any circularities or any gaps or any illicit hypotheses. And so in particular, you're not supposed to use anything related to the arithmetic operations, which are defined by the factors on which they are acting, and they're defined after the number. So you can see a little bit more clearly now what is the link between generality and rigor. And in addition of that, we have the idea that if the definitions are based on general concept, then this guarantees to have sure and complete demonstration. So if you base the concept of natural numbers, number itself on general notions, then you have a foundation that secures the definition that will follow, so the operation, the extension of the system of numbers, and all that comes with that. And you assure the reasoning without all the gaps and circularities and so on that you want to avoid if you want to be rigorous. So, but that doesn't tell us what rigor is actually about. So, an idea is proposed by Dedekind. So, Dedekind books on natural numbers. So the title asks what are the numbers and what is the role of the numbers. But the first sentence of the book is the following: in science, nothing capable of proof ought to be believed without a proof. And so the link with the definition of natural numbers is not the most evident. And so Dedekind proposed to interpret this statement as guiding what is acceptable to believe, what justification can be considered as valid for scientific proposition. He calls it Dedekind's principle, and so the idea is that the only proper and best possible scientific justification of a provable proposition is a proof, and you have to have a proof whose basic premises are unprovable. So Dedekind's principle gives us a standard of rigor in mathematics, according to which a proof is rigorous and therefore acceptable only if its premises are improvable. And that's what supports the definition of natural numbers. So of course, what's crucial here is that natural numbers for Dedekind are based on the so-called laws of pure thought, which are considered in the 19th century to be non-provable laws of thought. So, following Dedekind's principles, the improvability of the laws of sorts makes them perfect to serve as sort of ultimate premises for arithmetic. So here it's relatively easy to understand how Dedekind say on natural numbers answer to Dedekind's, the so-called Dedekind's principle. Since the building of the sequence of natural integer and all arithmetic will flow is based on the laws of sorts. But there is not a problem per se, but difficulty, that is, Dedekind is defining the natural number, he is not proving anything. So there seems to be a sort of ambiguity between to define and to prove. And so we should consider the possibility that the so-called Dedekind's principle is a demand of definition, and which would be supported. So on one hand, it would be supported by the fact that everything that Dedekind does is about defining a concept even when he does algebraic function theory. And another thing is in a letter to Lipschitz. So Lipschitz was a French mathematician who said to Dedekind that when he defines a good number by means of cuts, he doesn't do anything more than what is done in Eudoxus. So he said in Eudoxus theory. And so Dedekind isn't doing anything new, and he's in fact not doing anything good. So Dedekind defends himself, and he explained that if one wants to build arithmetic upon the concept of ratio of magnitude, which is not what is done in Euclid, then you cannot be content with the mere evidence that the magnitude exists, because in this way of funding arithmetic, the completeness of the concept of number depends uniquely on the concept, on the completeness of the concept of magnitude. But if you want to define if you want to build arithmetic scientifically, you need the continuity of the real numbers. And for this, you need to know at the beginning the degree of completeness of magnitudes. Because in mathematics, nothing is more dangerous than to admit distance without sufficient proof. But of course, defining magnitudes is something that we have never been able to do in any precise or rigorous way. So that just can't work. So you have to always have a definition or a proof of the distance. So this is where Dedekind's principle seems to play a role. So you verify or prove the hypothesis of resistance by effectively defining the notion of resistance you suppose by a systematic reduction to another concept. So concepts that have already been defined. And so to avoid gaps in circularities or even impossibilities in your proofs, you should never admit something that can be defined without a proper definition. So with Dedekind's principle, we have the idea that everything that can be reduced to simpler truths should be reduced to simpler truths. But you should keep in mind that you don't have to always go to the simplest of the simpler truths, and once you have defined a concept and you know it's rigorously defined, you can use it as a tool in further development of mathematics. So if you do such a reduction to earlier well-defined concept, then you assure the consistency of your concept. You can secure the inference and control each of them. So you justify and understand every step of your inferences, and so you your definition will allow for the proof to be rigorous, and then nothing susceptible of proof will be admitted without an actual proof. Okay, so that's that's the idea of rigor. So I will jump to generality because explaining how Dedekind actually does it takes a long time. So yeah, so that's what I was just saying. Dedekind has a very pragmatical goal in his foundational works, but in his mathematical work, he wants to give a definition that will be useful for future works, and so he is very explicit about that. It's often forgotten, but there is nothing foundationalist as we use it today in Dedekind's works. So what about generality? So I think there is a possibility that generality could be for Dedekind, not in any general way, a condition to rigor. So the idea is that the generality of the definition, as well as the generality of the theory, is dependent on the concept you use to define the concept. And so, if you use general concept to give a good foundation to the theory used to be, you will secure your proof. So that's what Dedekind does for natural numbers, for rational numbers, for algebraic numbers function, for algebraic numbers, for algebraic function. And so if you have the right general definition, then the proofs will be as general and they will follow more easily. So in practice, I'm not quite sure that they actually follow from series of simple logical inferences, but at the level of Dedekind's work, especially the foundational one, that works, more or less works. So asking for generality of definition is a guarantee of generality and rigor for the proofs, and you can even have better or new proofs. So Dedekind says that he is the first to give a rigorous proof that the product of square roots is equal to the square root of the product. And they give the first rigorous proof of the Riemann-Roch theorem, which is much more important than what Dedekind does with numbers. But another consequence, happy consequence of this, is that it will allow to secure future developments of mathematics. So if you do Riemannian function theory, you are much more certain to do rigorous and not maybe true things with a good definition of the elements of F than with a natural symmetric one. Yeah, okay, so rigor appears to be, as much as generality, an element that structures this practice of mathematics, and that's fruitful for further development of mathematics, contrary to what some people like Klein would say about being too rigorous. So, you can't really reduce the principle of rigor to a logical principle, especially insofar as it is so closely linked to the practice of mathematics and to the demand of generality. But you have the two following. On one hand, to base a theory on general notion will allow to satisfy Dedekind's principle, and you will effectively prove or define everything that is susceptible of proof or definition. And on the other hand, the definition is supposed to be general, so proof can be as general and made in one loop, as the definition is made in one, defines all the elements in one loop. So that way, everything that's before the definition is supposed to be true, and everything that is after the definition has to be made provable, and so we answer both the criteria of generality and rigor.